So basically what's going to happen in section 4.9 and pretty much all of chapter 5 is what's going to happen when I give you a function and I say that this is the derivative. How do you work backward to find your initial function? That's what we're going to be working with. Okay. It's kind of have two names. An antiderivative is basically a function where you know the derivative and you're working backward to find the original function. Okay. You could also talk about it in terms of integrals or integration. Okay. Chapter 5 is really the title of chapter 5 is integration. It ties right into finding an antiderivative. The antiderivative is really the function. Can you define a function? Integration is really finding the derivative along a certain integral. Okay. All right. So how does this apply? You know, say a physicist who knows the velocity of a particle wants to know position, right? Say you know the equation of velocity and you want to find the equation of position. Well, isn't the velocity the derivative of position? So I want to work backward to find position. Or say I had the acceleration function. Say I knew acceleration. How do you work backward to find velocity? Or how do you work backward to find position, right? Because we know the derivative of position is velocity and the derivative of velocity is acceleration. So how does that work? An engineer who can measure the variable rate at which water is leaking from a tank. So say you're able to measure the rate of change. What if you want to work backward to find the actual amount of water leaked over a certain period of time? Or say a biologist who knows the rate at which a bacteria population is increasing, but want to figure out the size of the actual population. How do you, if you know a rate, how do you work backward to find the original amount? That's what we're going to be working with antiderivatives. In each case, the problem is to find a function f whose derivative is known. Okay, and what we're going to be using is this capital letter notation. Okay, if I say capital letter, I'm saying that's the antiderivative. Okay, that's the antiderivative. If I say I've got a function f and I want to work backward to find the antiderivative, I'm going to use capital F to define that antiderivative. So here's our definition. A function f is called an antiderivative of f on an interval I if f prime of x is equal to f of x for all x in that interval. Okay? This is really the important statement here. If you can find a capital F and find the derivative of it, that'll get you back to the original. A lot of the homework problems say check your answer by finding the derivative. Right? That's just a suggestion, not a necessity. Okay? So you can always check your answer by finding the derivative. Always. You can always check your answer by finding the derivative. It should get you back to your original. Okay. So again, the goal here is that basically I'm going to be giving you a function. And I'm going to say, okay, this is the derivative. What's the original? You're always going to be working backward to find capital F. Okay. Now, let me ask you to consider this function. Consider the following. Consider f of x is equal to x squared. Let's take a basic parabola. What would the antiderivative be? What would the antiderivative? Or, maybe this is a better question, what type of function that when you take the derivative, you would get x squared? That's really what I'm asking. So a cube, right? Okay, well, we might say that, what if it's f is equal to x to the third? I just got done saying that this should be true. So let's find the derivative. Well, big F prime of x would be 3x squared. Did that come out to be just x squared? So what gets rid of that 3? Over 3. Over 3. Dividing by 3. Okay? Does that work? Does that work? Yes. Think about it. Let's take the derivative. That means f prime of x would be 3x squared divided by 3. Because do I need to worry about this divided by 3 at all when I take the derivative? No. That's like saying 1/3 times x to the third, right? So I bring it down and multiply. 1/3 of 3 is 1. Kick the power down. Just ends up being x squared. So what did we do? To find the antiderivative, instead of kicking the power down, I go up and I divided by that power. Right? I was saying I started with x squared. To work backward to find the antiderivative, I would kick the power up and then divide by that power, because that will reduce out when I take the derivative of it. Okay. We just did that first part. For instance, let f of x is equal to x squared. It isn't difficult to discover an antiderivative of f by keeping the power rule in mind. So big F of x would be 1/3 of x to the third. Now, you know what? Let me jump back to this slide for a second. What if I had said big F was 1/3 of x to the third plus 7? Does that change the derivative at all? No. It would still be x squared. Well, what about minus 4 or 5? Oh, I wrote a 5 and a 4. What about like minus 4? Does that change the derivative? No. The only thing that changed the derivative if I would have like added an x to that 4, right? So what does that mean? That means that, well, I could really add any constant to that antiderivative, and it would never change that initial function. Yeah.
Won't that change the position though?
It would change the position, but does that change the rate of change at all? Remember, think about the derivative. The derivative is the rate of change. So I'm not changing the slope of the line at all. I would change the original function where it would be. Right, and then if I gave you a coordinate, this is important, this is a good question to bring up. If I had given you a coordinate of the original function, then we can decide where it was going to end up. See, right now, if I'm given f of x is equal to x squared and I want to find the antiderivative, there's an infinite amount of possibilities for my original function, because I could always add any constant I would want here. Okay? The antiderivative always has to add a constant on the end. That's why, take a look here. If f is an antiderivative of f on an interval I, then the most general antiderivative is f of x plus c. You always have to add a constant on the end. Okay? Because that constant would have gotten taken care of when we find the derivative, it would just gone away. Right? So, and think about what that is graphically. What is a plus or minus a number sitting in the end? That's a vertical shift, isn't it? So all that plus or minus c is doing is just shifting it up or down. Okay? There's a graph in the book that I probably should have copied over. Heck, let's just pull it up. I was going to try to draw it, but why butcher it? Chapter 4. Let me show you here, because I think it's kind of cool. It's coming. I lied, it must have been earlier. Where is it? I'm getting closer. Oh. There it is. Take a look at that. Zoom in, please. Thank you. Take a look at all those functions. Okay? You know, all of those, if I take the derivative of all of these, this is x to the third over 3. This is just our antiderivative of x squared. Just changing the constant around. This is a plus 0, plus 1, plus 2, plus 3. This is a minus 1, minus 2. You know, you may be able to say, like, I know I'm kind of butchering it or using it loosely, you almost would say that they're parallel to one another at those times. Because if you take the slope at any given point, they would be parallel to one another, right? So you can kind of almost call them parallel-ish, but the only, yeah, I made that word up. But the only thing that it's changing, that plus C is changing, is the vertical shift up or down. It doesn't actually change the slope of the line at all. All it changes is the position where it is across the, along the x-axis, or the y-axis, excuse me. Now, there will be homework problems, and we'll do problems in here, in the notes, where I will tell you, okay, given f of 0 is some number, or given a coordinate based on the original function, you can tell where that c value would be, definitively, okay? If you want an arbitrary value, you call it c. But if I give you a coordinate, you can actually find the exact function of the antiderivative. Okay, let's jump back here. So let's take a look here. Find the most general antiderivatives for each of these functions. Okay, let's take A. A is f of x is equal to sine x. So what function, it's just kind of like guess and check. What function, when I take the derivative, is going to give me sine? Negative cosine. Yeah, you might be tempted to just say cosine, but what is the derivative of cosine? Negative sine, and I don't want negative sine, I want positive sine. So how do you flip that? Well, you just put a negative in front of it. Okay. If I take the derivative of big F, does it get us back to sine? Yes. Because the derivative of cosine is negative sine, and then we'll have negative sine, which would cancel out positive sine. One thing that we have to add on, plus a constant. Plus C, yep. Generally, we always just say plus C. Sometimes when we do double derivatives, double antiderivatives, we'll say plus C and then plus B. But usually for C, we're just making constant C. C? Bueno? C. All right, now this is a tricky one. Ooh, you're close. ln of x, natural log of x. Yeah. What gives 1 over x as its derivative? ln of x. Now, we have to be a little bit more particular about this. What is the domain of ln of x? Positive numbers, greater than 0. Okay, my original function, did I have a restriction on the domain? No, other than 0, right? But what takes care of that? The absolute value. Okay. Because my original domain was all, I could have negatives in my original domain. So I've got to be able to find a way to evaluate negatives. Well, to evaluate negatives, they work the same way as positives in that respect. So absolute value of x. Plus C. Plus a constant. Every single one of your answers, if I ask you for the general antiderivative, they should all end with plus C, plus a constant. So let's create a general rule for our power rule. So C says, okay, what if I've got f of x is equal to x to the n, as long as n is not -1, because if n was -1, it would turn back into ln of x, absolute value, ln of absolute value of x. So what's our general rule for a power rule? Well, we just kind of used it to figure out my antiderivative of x squared. That was kick the power up 1, and then divide by that power. That's the general power rule for an antiderivative. Take the power up 1 and divide by that number. That's why we took x to the third over 3. And then what should I do on the end? Plus a constant. It's going to be kind of like a running gag. You do plus a constant. Plus. That should be on every general antiderivative. So now this page is in the notes online. It might be a good idea to print this page for yourself. This is just a table of antiderivatives. You know, should you know all of these? Yeah, because we know derivatives, right? And we know them forward and backwards, right? So these are all, like say you had all of these as your originals, these would be the derivatives, right? Because these are the antiderivatives. So a couple things to point out there. Yeah, look, e to the x, remember? Yeah, man, that was it.
What a good.
I love you, e to the x. Way to go. Just staying, you do you stay the same, never change, e to the x. That's a joke, that was a good joke right there. Never change, man. E to the x. That's what you're writing in the yearbook, never change, e to the x. All right.
That should be like recorded.
Yeah, really? Yes. Be like e to the x. Never change. That's it. I got it. That's my new, what I'm gonna write in the yearbook. All right. Yeah, I know, really. We're getting nerdy. This is, if a constant is multiplied, the antiderivative would just be that constant to the antiderivative multiplied. Sum rule, again, the sum rule of derivatives works the same way as the sum rule of antiderivatives. You've got the trig ones up here as well, right? Think about inverse sine. There were all those weird inverse sine, inverse cosine, hyperbolic sine, hyperbolic cosine. Right? Remember all of those weird ones? This was like all of chapter 3, right? Working this way. Now we're working the other way. Right? We're finding the antiderivative. Okay? You know, this is kind of an interesting one here. If I've got b to the x, remember, think about the derivative of b to the x. The derivative of b to the x, like if I look at, oh, this is still up here. My derivative rules. My derivative of b to the x, d over dx of b to the x is b to the x ln of b. Okay, so to undo that antiderivative, work backward, b to the x divided by ln of b rather than multiplied by ln of b. And that's an interesting one there. These are very special cases here and here. 1 over the square root of minus, 1 over the square root of 1 minus x squared is inverse sine. 1 over 1 plus x squared is inverse tangent. Okay. All right, so find all functions g such that g prime is 4 sine x plus 2 x to the 5th minus the square root of x, all divided by x. So again, I'm given my derivative. I'm asked to work backward to find my original. Now, a lot of these problems are going to require you to kind of simplify it down at the beginning so that taking the antiderivative is a little bit easier. You want to simplify it down at the beginning so that you can take the antiderivative easier. Now, let's start off by doing this. What's the antiderivative of 4 sine x? Well, the constant multiplied in front is going to stay. So what's the antiderivative of sine x? Negative cosine x, right? I'll take it step by step. So really, this is just going to turn into negative 4 cosine x. That was an easy piece. How did we know it was negative cosine? Well, remember, it's got to switch the negative to positive, right? If I take the derivative of just cosine, it would be negative sine. So I want it to be negative cosine then. So it would be negative sine and positive sine. Now, I am going to reduce this down a little bit. Okay, this chunk in here, I'm going to reduce that just a little bit. How am I going to do that? Well, I'm going to split apart the fraction. Always try to break it down to be a power rule, because the power rule is the easiest one to use. I think we've seen that with all derivatives, right? Power rule is always going to be the easiest one to use. So this is going to be a 2x to the fourth minus, well, this was a x to the 1/2 over x to the first, right? Because the square root of x is 1/2 power. So that's really going to reduce down into 2x to the fourth minus x to the negative 1/2. You follow me there? 1/2 minus 1. All right, so now we've reduced it down that we can find the antiderivative using a power rule. What that means is now I take the 2x, kick the power up 1 unit, divide by the power. Minus, kick the power up 1 whole unit, negative 1/2 turns into positive 1/2, and divide by that power. So now let's bring everything down now. So big F is negative 4 cosine x plus, and we'll just make it a fraction out front, 2/5 x to the fifth. Now, what is dividing by 1/2? Multiplying by 2, right? So minus 2 x to the 1/2. Plus c. The only thing you could do there is take the x to the 1/2 and turn it back into a square root of x if you'd like to, but I would accept it either way. See what I'm getting at there? You could make that x to the 1/2 turn it back into a square root of x. 6 to 1, half dozen the other. What's wrong? Divided by 1/2. Dividing by 1/2 is the same thing as multiplying by 2. So I just turned that into a 2 x to the 1/2. Okay. Questions about that? No? Okay, let's keep it going. Yeah, I know, there's no example here, I took that.
No, I still don't.
You still don't get why I got the 2?
No, I just can't.
Yeah, keep change flip. 1 divided by 1/2 is 1 times 2 over 1. Does that make sense? Okay. Yeah, no example 3. I took example 3 out. It's too weird. That's a weird negative exponent from John Tyler. Now look at what I've got here in example 4. Find f given f double prime. But I'm also given f of 0 is 4 and f of 1 is 1. So I'm given some information about my original function, which will allow me to find my constant. See, I'm not going to need to find a general antiderivative for this one. I mean, I will, but in the end, that's not going to be my answer. My answer I will be able to solve for those constants sitting at the end of my antiderivative. All right, so let's find f prime. Look, this is a nice one because that's just a polynomial. Sweet. Polynomials are nice. So that means f prime of x is going to be, all right, kick the power up, x to the third, divide by that power, 3. Soon enough, we will do enough of these that you don't have to write the 12 over 3. You can just make it 4 right away. But I'm going to show all the work here at the beginning of this. Plus 6x squared divided by 2 minus 4x. Right? And I could say divided by 1, but I don't need to.
Just add x to the.
Yep, you just add x to it. Because you take the power from x to the 0 up to x to the first, and then you divide by 1. So really just add the x. Plus a constant. All right, so let's reduce that a little bit. F prime of x is 4x to the third plus 3x squared minus 4x plus c. And now we find f. Okay, f is that now going to be 4x to the fourth divided by 4 plus 3x to the third divided by 3 minus 4x squared divided by 2 plus cx plus a different constant, d. If we keep adding different constants, we just change the letter. C, D, E, F, whatever, how many derivatives we have. Okay, so let's reduce it. F of x is going to be equal to x to the fourth plus x to the third minus 2x squared plus cx plus d. Now, if I wanted a general antiderivative, that would be my answer. But I'm given more information. I'm given that f of 0 is 4, and then I'm given that f of 1 is 1. I don't know how we came up with that, but that's given within the problem. Now, this f of 0 being 4, that's a very useful piece of information there. What does that tell me? The y-intercept 4, what value is that within my original? D. This tells me that D is 4. Because meaning, if I plug 0 in for x, the y value is going to be 4. So 0, 0, 0, 0, 0 plus D is equal to 4. So I know that D is equal to 4. So that means f of x is equal to x to the fourth plus x to the third minus 2x squared plus cx plus 4. And now that last piece of information is going to tell me what my C value is. It's not just as simple saying that C is 1, though. You've got to plug 1 in. So f of 1 is going to be 1 to the fourth plus 1 to the third minus 2 times 1 squared plus C times 1 plus 4 is 1. That make sense? All right, now let's calculate it out. That's a 1 plus 1 minus 2 plus C plus 4 is 1. Okay, that will all cancel. 1 plus 1 is 2 minus 2 cancels. Subtract the 4 over, C is negative 3. So now my unique antiderivative, not general antiderivative, my unique original function is x to the fourth plus x to the third minus 2x squared plus, minus 3x plus 4. Does that make sense? Again, the more we know derivatives, the more we know about antiderivatives. Right? The more we know about derivatives, the more we know about antiderivatives. One of the key pieces of information that we needed, we've already really talked about the next example that we're going to do. One of the things that we need to do within section 4.6 was, and especially on your test, look at the function's derivative and then tell what you know about the original. See, we were already kind of working with antiderivatives, but we didn't even know what they were called, that they were called antiderivatives yet. You know, on that question on the test where I said, what do you tell, how can you tell, you know, is it increasing, is it decreasing? Just given the graph of f prime. Now we're going to take it one step further and say, the graph is given, but that's the graph of f. Graph the original. That's the graph of f, graph the original. Now, we have already gone through the process. We should know what, if this is the graph of the derivative, what are the implications on the graph of the original, right? So let's kind of go through those pieces. What do those two pieces tell you? If this is the graph of the derivative, what do those two pieces tell you? The minimums and maximums, the extreme values. What is this one? Well, it's going from, look, it's decreasing down below, increasing above. It's going from decreasing to increasing. Minimum value. There's a minimum value there. Do we know where it actually occurs? No, we know that it's at x equals 1, but we're not exactly sure where it occurs. This is a maximum point. We know from 1 to 2, the function is increasing. We know from, at least looks like it stops at 0, 0 to 1, that's a parenthesis, 0 to 1, and from 3 on, oh, I'm sorry, 0 to 3, for increasing. From 3 on, that it's decreasing, because it stays below the x-axis. What can we tell here and here? Those are inflection points. These are inflection points. Whatever. Those are inflection points. What can we tell about this? What is that telling me? Concave up. From 0 to 2, it's concave up. Concave down, oh, and also, I guess I should say, from 4 on, it's increasing, right? So from 4 to infinity. From 2 to 4, it's concave downward. So what does that tell me? How do I graph the original then? Well, I've got to have a starting point. Good thing they told me. Big F of 0 is 2. Oops, I'll just flip. This is F. F of 0 is 2. And then it goes from 0 to 1. It's decreasing until it hits my minimum point at 1. So let's say we need 1, 2, 3, 4, 5, sure. At 0, at 1, at x equals 1, it hits a minimum point. So let's say that it bottoms out right there. At 2, there's an inflection, reaching a maximum at 3. So 2 inflection, let's say it goes up to here. At 4, there's an inflection, and then it will decrease forever. Staying concave upward from 4 to infinity. Right? Do we see the inflection points in here and here? Now, could I have made those minimums and maximums like stretch out? Yeah, I didn't necessarily know where those were occurring. I just knew that they were going to occur at those x values. Same thing with the inflection points. I could have made them higher or lower on the graph, but you know, I don't necessarily know exactly where they are. That makes sense? We kind of already did that, right? The only thing we didn't do was sketch the graph on top of it, like to see what the actual antiderivative would look like. All right, we'll stop there for today. We'll pick up the rest tomorrow. Sound good?